you've got 3 sections to the day's lab. You get a section with questions. You get a section to put your answers to those questions down, the one with all the boxes on it. That's what I'm expecting you to fill out and turn in. And this is all building to you being able to design your own hypothetical experiments, and also being able to critique somebody else's hypothetical experiments. So that's the 3rd section. And that's separate because at some point, you're somehow gonna need to trade them off to your partner so that they can critique it and give it back to you. How do you do that remotely, I'm not entirely sure, but yeah, I have confidence that you guys will figure it out. So for this first part, you've got the part with all the boxes. This is the way a lot of our discussion labs work. We're gonna work our way through it. We're gonna get answers from the group, and I'm expecting you to write those answers down as we go along. Sometimes we get a lot of answers from the group, and if we get like a long list of things, I don't expect you to put it all down. But I do expect you to have an answer for every question when I go to correct it. So take a look, ready to write stuff down. From the science chapter, anybody gotten to the point? Can you tell me what are the 3 fundamentally different ways that observations can get made? This is one of the problems with having lectures remote, is that you will find if you leave them all to the end of the month, you will never be able to get through them in the time you're gonna need in order to do the exams. So by now you ought to be looking at least a couple of days worth. Actually, we would have had 3 lectures before now. We would have gotten through into the 2nd chapter. This is the 2nd chapter. Observations, ways to take information in from the world. You got to do that to start with, because the whole idea of a hypothesis is you observe something and then you're trying to explain why it happens. Anybody want to take a shot as to a way an observation could get made?
I've seen it.
Okay. You can make your own personal observations, right? With your own personal senses. That is one fundamentally basic way of making observations. Your own personal see it, hear it, taste it, whatever. But that isn't the only way we take in information about the world, is it? What's another way that's different?
Observing data.
Hmm?
Observing data.
Well, you can't observe
I
data.
mean, like analyzing like a bunch of.
Well, analyzing is different than observing. Analyzing is much farther down the road. Is that, now sometimes, somebody else's data you're looking at, and you're going, well, I think I see something here that they're not seeing. That's a type of observation. It's a second-hand observation. It's their data, right? They're the ones that saw it and put it together. And that's another way of doing observing. Observing secondhand from somebody else. And that often happens in research, where you're looking at a paper, and you get all the way through it, and you get to their conclusions, and you go, really? That's what you got out of this? I've been coming up with a different idea all the way through this, and you've gone in another direction. But that's how science works. That's why it's an observation that can lead to an explanation. Yours just turned out to be different from theirs. So that's a different secondhand observation. Somebody tells you something, you read something. Now the 3rd one's trickier, and I'm not expecting anybody to come up with it if you haven't heard it before. Microscope. It shows me things I can't personally see with my own personal senses. But I have to trust that it's working right when I'm using a microscope, that I'm actually seeing what's actually there through the microscope. Now, that's just one type. The 3rd type of observation is using some sort of device to observe things about the world that we cannot personally observe with our own senses. So whether it's a microscope or a telescope or an oscilloscope, an MRI machine is is that any sort of device that gives you information, you always have to trust that the device is actually giving you reliable information. That's why firsthand observations we kind of trust. It turns out we're not that great at making firsthand observations, but we trust our senses. Secondhand, you never know, right? You never know if what you're hearing or what you're reading is what really happened. So they're a little bit less trustworthy. Devices, we trust them. Sometimes we shouldn't, but we trust them. And there are times where somebody will come and go, well, did you do this with that device? Yeah. Oh, that's why you got that result, because that's not what it's supposed to do. So sometimes the devices will come back and bite us. As I said, this is all going to build explanations. If you've got a sciencey mind, you can't help yourself. You see and hear stuff, and your brain goes, oh, I wonder why that's happening, and then you try to come up with reasons. Now, for a hypothesis to be a good science hypothesis, it has two features it's got to have that are very much connected to each other. Anybody know what those are? Hmm? I don't hear well, so sometimes I have to get close. Not necessarily. They don't necessarily have to hold up logically. In order to get other people to listen to you, they have to hold up logically. Now that I'm running he said cause and effect. There is an aspect that absolutely relies on cause and effect, and let me see if this is what you meant. You ought to be able to take your explanation and say, well, if this is true, then this should happen, right? Is that they call that being predictive. You know, I can take my explanation and use it to make predictions about what should happen. Because if it isn't predictive, then you don't have the second feature that's absolutely is needed. Anybody know what the second feature is? You're talking to another sciencey person and you go, here's my idea. And they go, really? How do you fill in the blank? Well, no, if we're good sciencey people, we never use the word prove. Somebody else said something. How do you test it? Is that if you've got a wonderful hypothesis, but there is no way anybody can come up with to reasonably test it, then it's just a nice idea. And the thing is, if it isn't predictive, you can't design a test, right? You can't say if this, then that, cause and effect. So the predictive very much connects to the testability. And that gets tricky. When Einstein decided that gravity was a curvature of space, well, it was physics, so people didn't really say, how do you test that? They went, what does the math look like? Physics is weird. But some people said, so, Albert, how do you test that? And he goes, well, I can give you a way to test it, but you're not going to be able to do it anytime soon because it involves solar eclipses. And something like 17 years later, somebody actually did show that when the moon gets in front of the sun and blocks the light, that the positions of the stars right next to the sun are in a different spot than they're supposed to because the light coming past the sun got curved because the space next to the sun was curved. But they'd already pretty much accepted Einstein's theory of gravity by then. Because physics people, they often will take the math as a test. So, we're down to the next box. Somebody give me an observation just made in here. Something. The water's running. Now, is that an observation or is that a hypothesis?
Observation. Observation.
Well, where's the water running? So you are assuming it's running based on what you can hear. So you can hear what it sounds like water running. Now that's your observation. You get into a little bit of trouble where somebody goes, what do you mean it's running? You know, do you think somebody's got a faucet turned on? Because that's usually what people mean when they use the word running. And wording starts to become an issue when you make an observation, because the way you state your observation may not always connect to what other people use for the same wording. But she's absolutely right, right? You can hear what appears to be water running. Now, you're not where you can see it. So your observation is a little bit disconnected from what's there. Just some of you can see there's water running back there in the tank. But that's a testable. Well, if we take the observation that it sounds like there's water running somewhere, that kind of leads right into a hypothesis, right? When you're dealing with real world stuff that's right in the room with you, a lot of times the observation and the hypothesis are very much linked. And you hear what sounds like water running. Now I could be recording something in the back. You know, maybe in the morning I like background noise, and I've got one of these nature sound things running. So you don't know for sure that it's actual water running. But your hypothesis is that there's actual water running in the lab, right? So that's a hypothesis. And it's a testable one, right? How do you test it? Yeah, you wander around till you figure out where the sound's coming from and see if it's actual physical water running. When you're doing these kinds of things, it turns out they turn out to be pretty simple observations and hypotheses and tests. Somebody give me another one, another observation.
The snake is asleep.
The snake is, you see, the fact that you said is it means you have not an observation, but a hypothesis. Now, what did you observe that made you think the snake is asleep? It's not moving, right? It hasn't been moving for a while. So that's your observation, that as long as you've been here, that snake's been in the same position. Your hypothesis is that she's asleep. Is there any way to test that?
Why everything broken?
Now I could do something and she would move, but you just came up with a hypothesis that's really tricky to test. Because if I do something and she moves, does that really mean she was asleep before she moved? That's a tough one. I mean, you can test it that way, and you can absolutely say, she's not moving now, she's asleep. If you do something to the tank and she moves, she wakes up. And what often happens in science is people go, no, I don't think that's what was going on. I think she was just resting. I don't, look, her eyes are open, and you go, well, yeah, they can't close their eyes. That makes it really tough to tell. And some people may go, I don't even think snakes sleep. Now, there's another hypothesis. I'm not sure how you would test that, but that's what you wind up with. The snake's not moving, observation. She's asleep, hypothesis. You can come up with a few ways to test it, but people might criticize your definitions and your testing. But that's part of science. Doesn't make it wrong, just makes it questionable, as in people can question it. I need a third observation. Anybody? No, he keeps tearing down stuff that people said.
There are 7 students in here.
Say again?
There are 7 students in here.
Simple, 7 students in here. That involves data, right? At the counter. Anybody got a hypothesis based on there being 7 students in the room? You could come up with a bunch of those.
students, then the rest are at home.
Okay. If there's 7 students in here, then the rest of the people that were here last week must be home. Pretty simple hypothesis, a testable hypothesis, right? You can come up with a test for that. Okay, so we've got our observations, we've got our possible hypotheses, we've got our possible tests. Just to give you an idea how this works. You did actually pretty good there. Sometimes people's observations are very much embedded with hypotheses, and the only thing we really got was the assumption of a sleep, and that really wasn't a bad embedment. Anybody remember, you should have had this in high school. What's meant by the variable in an experiment? That is something that changes. Well, yeah, but a little bit more than that. Anybody remember? A lot of the tests that are being done, like right now, there's a lot of criticism of using convalescent plasma of people who have recovered and have antibodies as a treatment for people that are advanced COVID. And one of the issues is they've used it a bunch of places and they've gotten good results, but there's no comparison group. They can't really compare this treatment to a really good comparison group. And the convalescent plasma treatment winds up being the variable. To test it effectively, you should be like, okay, we're gonna, centrifuge the plasma down until it's just this kind of slurry that we're gonna inject into people. We should be taking an equal number of people in the same situations and injecting them with something that isn't convalescent plasma, but is close enough to the appearance of it that the people getting it think that they're getting the same treatment, a placebo. You need your comparison group, or sometimes multiple comparison groups. And what changes from one group to the other is your variable. And that's gonna come up again and again and again today, where we're gonna look at potential tests and I'm gonna go, okay, what's the variable here? Because if you're designing an experiment, the very first thing you need to know is, okay, what am I gonna change between one test and the other? Now, sometimes if you've taken a science class, they throw a couple of different types of variables at you. They throw the dependent variable at you, the independent variable at you. I will tell you that people who work in science, if they talk about the variable, the only thing they're talking about is the independent variable, which is the experimental variable. What's changing between your tests? Now, to get to number 2, I just gave you an example of a very classic experimental variable. Convalescent plasma, the variable is actually the antibody mix in the plasma. And if I'm gonna set up a placebo group and then give them an injection, I want them not to be getting a mixture of antibodies. I want it completely out of there. A classic experimental variable is one that you could completely remove. And in drug tests, that turns out to be not that difficult to do. You give somebody a pill with a chemical in it that you're testing, you give your placebo group a duplicate pill, it just doesn't have the chemical in it. You've taken the chemical out. But you can't always do that. Say we're testing the effects of temperature on plant growth. You can vary the temperature between your groups, but you can't take it away. You can't grow a plant at absolute 0. So sometimes the variable really does just vary, and in that case, you probably would do a number of different variations on temperature. But the classic ones you can actually take completely away. It just doesn't happen that often that you can do that. And when you're coming up with variables that are not removable, then it's a matter of, well, how much do we need to change them? Like, okay, I'm gonna do an experiment on light intensity and plant growth. I could do a test with the light completely removed. I could try to grow some plants in a closet, but I kind of know going in that that's not going to be a terribly useful comparison. So it doesn't even make any sense to do that variation, that particular, what they call control group. When you change your variable, your comparison group's called your control group. And that's gonna get us into the next part. And I'm gonna stop this.